Hi, this is Yogesh Langde, and in this video, we will see a numerical on thermal radiation for a single cylinder and a concentric pipe. Let's see the statement of it. A pipe carrying a steam, an outside diameter of 200 millimeter run in a large room and is exposed to air at a temperature of 303. The pipe surface temperature is 673 Kelvin. Calculate the loss of heat to the surrounding per meter length of a pipe due to the thermal radiation. The emissivity of the pipe material is zero point 0.8. Also, what would be the loss of heat due to the radiation if the pipe is enclosed in a 400 millimeter diameter break channel of emissivity 0.91? So here we need to calculate. The first approach is to case 1, where we say the calculate the heat loss of through the pipe per unit length to the surrounding. And the second thing, what would be the loss of heat due to the radiation? If when there is a radiation, that time pipe is enclosed into the brick channel. That time, what would be the heat losses? So let's, with the help of the diagram and all, we will see how these things behave. So let's consider this is a room. In this room, there is a cylindrical pipe through which the steam is flowing. The T1 is the temperature of surrounding, means in the room, and T2, which is the temperature of pipe, which is a 673. Okay, now this is the condition, first condition. So this is the first condition. Just take this is it is 673. Okay, now the temp. This is the first condition, and from this one, the radiations is happened. So the radiations is takes place through this pipe to the surrounding. So the heat losses from the by the thermal radiation by the pipe to the surrounding one. Now this is the first case. What is the second case? The second case is that in the room there is a pipe through which the steam is flowing. So from this one, the steam is flowing, and on that one another concentric pipe of brick material is placed. At this time, what is the heat losses from this pipe to the concentric pipe? Now the concentric pipe, which is brick channel, is again at a temperature, what is the room temperature, and the temperature of the steam, that is the surface temperature of this inner pipe, which is a 673. Okay, now this is the case. So in the first case, there is only we have a single pipe to be here in the room. This is the first condition. In the second condition, there is a pipe. Only that changes be there. So the case 1 and case 2, for that one, how we can go for that one? Let's see. So, so data, we write the data of it. So diameter of the pipe is given 200 millimeter, convert into the meter. Diameter of the brick channel, that is the concentric channel on the pipe, which is a 400 millimeter, which is zero point 0.4 meter. Temperature of the room is given 303 Kelvin, and temperature of the pipe surface, that is inner pipe, which we say it is 673. So 673 is the temperature. Now the emissivity of the pipe is given E1 zero point 0.8 and emissivity of the brick channel, which is given 0.9. So this is the data. As I said earlier, with the help of that diagram, we see there is a two cases. What is the one case? In the one case, only the pipes, inner pipe is loses the heat by the thermal radiation into the room. While in the second case, the pipe is surrounded by another pipe. And for that one, how the heat losses is takes place from the inner pipe to the concentric pipe. So for the first case, when there is only the single pipe, which is directly radiate the heat to the room, is this one. So Q heat losses is equals to the E1, that is the emissivity of a pipe, into the sigma, that is the Stefan-Boltzmann constant, into the A, area of the inner pipe, into the T1 raised to the power 4 minus T2 raised to the power 4 Okay, where here is again the one change be there, that is T1 is the 673 and T2 is the 303. Just make that changes is here. Okay, so this is T2 and this is the T1. So T1 raised to the power 4 minus T2 raised to the power 4. This is the first case. What is in the second case? Second case is it is that the concentric pipe is there. So there is a two pipes. So for that one we can write a formula Q is equal to sigma A1 area of the inner pipe into the T1 raised to the power 4 minus T2 raised to the power 4 upon 1 upon even emissivity of the pipe plus the emissivity of the brick, as it is a concentric pipe as shown in the figure. Okay, and that is this D1 by D2. D1 is the diameter of the pipe and D2 is the diameter of brick channel which is on the that pipe one. So this is the numerical, as again I show you that how the things is there. This is the second one, as this pipe, as I said, this is the pipe, and on this one another pipe is there. Okay, this is the second condition, and this is the first condition. Directly it is exposed to the room. Okay, so let's see how to solve this numerical with the help of that one. And here is we have this approach. Let's write the data. Already I show you the data. Now we will try to solve this numerical. Okay, so let's see that as per the data which is being mentioned, we already write down the data, and there is a small conversion, as I said, millimeter into the meter. Now we will move for the first case, the case 1, and the case 1 is that pipe to surrounding. The heat losses from the pipe to the surrounding, that is into the room 1. Okay, so this is a first condition be that, and for that one we have the formula, that is Q is equals to the E1, the emissivity of the pipe, into the sigma into the area A1 into the T1 raised to the power 4 minus T2 raised to the power 4. Just remember one thing, that here the T1 value which is shown in the previous data is T1 is 673. Just remember this is the correct one, 673, and T2 that is to the room which is the 303 Kelvin. Just remember this part. Okay, wrongly I just shown in the last slide. But now emissivity is given to us. Sigma is the Stephen Boltzmann constant. Area. What is the area? Area of a inner pipe. What is that pipe? Initially, it is area, surface area pi into the D1 into the L. So we need to find with respect to the length. So Q by L, that is to be there. So we can write E1 into the sigma into the area is pi into D1 into the L, already I am taken here, into T1 raised to the power 4 minus T2 raised to the power 4. Okay, so we just put it the values of it because everything is with us, and for that one we just put the value. What is the emissivity? E1 of the pipe is given zero point 0.8, so I'm just taking here zero point 0.8. Sigma value is constant 5.67 into 10 raised to the power minus 8 into the pi, which is the constant value, into the D1 is zero point 0.2 diameter of pipe, into the temperature it is 673 raised to the power 4 minus 303 raised to the power 4. So once we calculate this part, we get per unit length, and that value is around 5603. It is in a watt per meter. So this is the answer of first case. Okay, so this is the answer of the first case. Now we move for the second case. What is the second case mentioned? The second case is that in the second case we have case 2. In the case 2, we write the concentric pipe, concentric cylinder. So concentric cylinder. Okay. So in this one, what happened? There is a pipe, and on that one, another pipe is there. So here, steam is flowing through this one, and radiation is happened from this pipe, okay, to the this concentric pipe. So in between, the heat is transferred between these two, and for that one, we can write the formula Q is equals to the sigma into the area A1 into the T1 raised to the power 4 minus T2 raised to the power 4 upon, as it is a concentric cylinder, that's why we are writing the formula of it, 1 upon E1 plus it is A1 by A2 in bracket 1 upon E2 minus 1. And this is again rearrange the area in such a way that sigma into the A1, already we calculate this value, into the T1 raised to the power 4 minus T2 raised to the power 4 upon, we can write as 1 upon E1 plus D1 upon D2, diameter of pipe to the diameter of brick duct, into 1 upon E2 minus 1. Now, as I said, this area, already we write that area A1 is the pi into D1 into the L, and this L I am taking here. So I can write this equation as Q by L is equals to the sigma into the pi into the D1 into the temperature difference of it, T1 raised to the power 4 minus T2 raised to the power 4 upon the same thing in the denominator, which is 1 upon E1 plus D1 by T2 into 1 upon E2 minus 1. So we just put it the values of all these one, and to put it the values, we know the values of it. So Q by L is equals to the value of sigma is 5.67 into 10 raised to the power minus 8. D1 pi is constant into the D is the diameter of the pipe, 0.2 inner diameter, into the T1 is 673 raised to the power 4 minus 303 raised to the power 4 upon upon 1 upon E1 value is 0.8 plus D1 value is 0.2, D2 value is zero point 0.4 into the 1 upon E1, E2, which is the 0.91 minus 1. Okay, so we got a value of this one, Q by L, when there is a concentric pipe, is around 5391. 5391, around this value to watt per meter. So this is the heat losses when there is a concentric pipe. Now, if I want to know what is the reduction in heat losses, if I want to calculate on that one, what is the reduction in heat losses? If the question is like that, the heat losses, reduction in heat losses when there is a concentric pipe and when there is a surrounding one. So the reduction in heat loss, then for the first case, when there is the pipe is exposed to the surrounding, that time the value is 5603, and when it is to be there, it is 5391. So we can see there is around the change in the value is that let the value is changed as 5603 minus 5391. So around 212 is the reduction in the heat losses per unit length of this one. So here that this is a second answer, right? The case 2 answer is this one, and the reduction in heat losses we got a value is around 212. Thank you.